We've seen that the fact that the magnetic field has zero divergence mathematically means that you can write the magnetic field as the curl of a potential, a vector field we call the vector potential. Let's deal with the same thing for electric field. One thing we noted in that derivation was that the curl of the electric field when it's static, I'll say ST for static, when there's no time dependence on anything, Maxwell's curl equation for E says that it's zero. And we asserted that that's the reason why the electric field in a static situation, like when you first learned about electric fields, like in Coulomb's law, and nothing was changing in time, that it could be written as the grad of a scalar field psi, which in electrostatics we call the voltage. Now the problem is that we're dealing with electrodynamics, and in electrodynamics the curl of E in general, if you remember Maxwell's curl equation in general, is equal to the negative time derivative of the magnetic field. And that, of course, is not equal to zero. So this leads to us to the problem that we can't write this as a potential. We cannot write the electric field simply as the gradient of a scalar potential. So what do? Well, it turns out it's not that hard to get the math to behave somewhat similarly. Because if you just take this equation here and you bring both terms to the left-hand side, obviously you'll get something equal to zero. So the curl of E plus dB dt is obviously equal to zero. Okay, but can we get the entire left-hand side to look like the curl of one thing, so that the curl of that one thing can be written as a grad? Well, let's substitute in. Now we make use of the fact that the magnetic field is a curl. So I can rewrite this as curl of electric field plus time derivative of the curl of the vector potential. That equals zero. And now, because these fields are continuous and smooth, you can exchange time and space derivatives. You almost always can do that. And so now this becomes the curl of E plus, now I'll reverse the order, it becomes the curl of dA dt. And that, I can just group these terms, becomes the curl of E plus dA dt and that equals zero. So now this E plus dA dt is going to play the role of E static. This allows us to say that E plus this extra term dA dt, it must be that this can be written as the negative grad of a potential field, a scalar field we're going to call psi. It's not, of course, the same psi that you'd get in electrostatics, but it's just some scalar field. I'm going to keep using that variable for familiarity. And now I can just solve for this. So although the electric field itself is not equal to a grad of psi, E plus dA dt is equal to grad of psi, and if I isolate E by itself, I get that electric field is equal to the negative gradient of a scalar potential minus the time derivative of the same potential that the magnetic field is a curl of. And notice that in the case where there's no time dependence, then dA dt would go to zero, and you would recover the electrostatic case. So this is a more general case that's true. This, of course, was a more specific case.